Hi, everyone. I am Katie from Hackster. Welcome to the Acoustic Sensing and Environmental Monitoring with Embedded Machine Learning webinar with Edge Impulse and Texas Instruments. Well, we've got David Schwartz here today with us to share more about how you can use Edge Impulse to design and deploy an environmental monitoring system that detects and identifies anomalous sounds using the TI CC1352P LaunchPad. So a little bit more about David. David is a user success engineer at Edge Impulse. He's helping customers build and deploy products powered by machine learning. He is a University of Texas graduate with previous experience in embedded systems design and applications engineering. He lives in Austin, Texas, and enjoys reading, swimming, and programming in his spare time. So a little bit about how today will work. The first 45 minutes of today's webinar will be a presentation followed by a demo. And then the last 15 minutes will be open for your questions. So if you do have questions throughout the webinar, there's a little Q&A section at the bottom of your screen. You can write your questions in there. That way we don't miss them in the chat. And David will get to as many of those as he can before the end of the session. So thanks again for joining us. And David, I'm gonna let you take it from here.
Thanks so much, Katie. So hi, everyone. Thank you for joining this talk. We here at Edge Impulse recently partnered with Texas Instruments to bring TinyML to their low-power wireless IoT devices. And today I'll be showcasing how you can combine their hardware with our software platform to create robust machine learning-powered applications. So specifically, today we're going to be designing an example acoustic monitoring tool. We're going to be trying to detect the sound of glass breaking. So think of this from a security or safety point of view, trying to pick up when a pane of glass, a window, or something like that is broken into. And we're going to try and make a model that's robust against other real world conditions, things like people talking, other loud noises, cars driving by, real world factors that the model would be exposed to if it was deployed in, say, a smart home. So in order to do this kind of demo, I'll first give a technical overview of what we do here at Edge Impulse and also the TI hardware that we'll be working with. And then I'd like to spend the rest of the time doing a live demo of kind of how you would go through Edge Impulse to design such a model and how you deploy it to the Texas Instruments LaunchPad. And then we'll see how it performs once we get it running on the device. So to start, let me give a little bit of background about who we are, what Edge Impulse is, and kind of what we do. So we're the leading platform for embedded machine learning. We provide software to collect data, train machine learning algorithms, and deploy them to embedded devices like the Texas Instruments LaunchPads. We take this capability and we put it in the hands of any engineer or designer. You don't need to be a data scientist to use our tools. And everything's completely free for developers to try out and prototype new designs. We're a completely open source platform in terms of the code and algorithms that we use, so nothing's kind of closed off to the users. And our platform's been tested with over 50,000 developers and 35,000 projects already. So what Edge Impulse really enables users to do is to add intelligence to IoT and embedded products that previously might have operated in a simpler workflow of collecting data and then just transmitting that data to a host system or data center in order to process it there. And I'll talk about some of the challenges and kind of advantages that you get from using embedded ML in the next couple of slides. But the main thing that we do is that by running an ML algorithm on the edge device, you're able to have that device using its local processing detect and notify you only of important events, only of things that you care about. And this is made possible by a shift from kind of rules-based engineering. Here's a fun little GIF of our founders doing kind of a live coding session where they're programming an algorithm kind of the old-fashioned way, where you might detect certain frequencies of a sound that you're trying to pick up. So in this case, the sound of glass breaking, something like that. Or even if you can't develop an algorithm for it, putting a human in the loop by actually streaming the data to a person who's actively manually classifying, okay, what's going on here? Think like a traditional security system with like a CCTV, right? And so the issue with this model and where TinyML can really, and embedded machine learning can really add value is in situations where it's really expensive to either have a human design that new algorithm or actively monitor that data, or it's not practically possible. And so what we replace this with is this kind of data-driven engineering loop, where on device, you collect sensor data from the real world. You determine, okay, what interesting events am I looking for? What interesting things will this sensor encounter in the real world? And then you iteratively design that algorithm using machine learning techniques to detect those interesting events. And when the device is exposed to new contexts, new environmental factors, or new interesting events that you want to detect, you don't have to go back to the drawing board and design a new algorithm or train an operator to detect those new things. It's just built into that development loop of adding new data and then running training and redeploying to the device. And so this allows for a very iterative kind of development cycle where you can start with a prototype like what I'll be showing here, where with a few minutes of data, we're able to create you'll see a decently robust model. And then from here, depending on what context this device might be used in the real world, depending on what factors and kind of what things it needs to make sure that it is able to properly detect, you'd be able to add new data and improve the model further from there. So nothing's a black box, nothing's locked down, everything can kind of improve and develop over time as you learn more about your system and about the data that you have. So this iterative style of data-driven development has shown to be very useful in a lot of different applications, from embedded vision, computer vision, predictive maintenance in both industrial and kind of home applications, human interfaces, things like voice recognition, detecting keywords, and then industrial use cases, detecting defects in a product, detecting safety hazards, things like that. And so I'll give a little bit of the technology overview of how Edge Impulse works, but I'll try to show most of this live during the demo portion, but just to give kind of a brief overview. Our main kind of loop that I mentioned before, that iterative process, is giving the ability to collect live sensor data off of real devices in the field, run training, machine learning techniques to kind of train an algorithm, which we call an impulse. And then you validate the performance of that impulse against different test cases, just like you would normal software. And then you redeploy it. And that whole loop is contained within the Edge Impulse ecosystem, as you'll see in just a little bit. And you're able to, from there, like I mentioned, just iteratively improve a model. And all you really need to do is kind of constantly have that ability to collect data, bring it into the platform, and use it to improve the tools that you're working with. So how do we do this? We try to make it as easy as possible to collect data from a variety of sources and for a variety of different kind of starting points. So users might come from a situation where they're working off of a publicly available data set, which as we'll see in a little bit, I'm using today. But you might also want to then collect live data off of a device using the exact same sensors and techniques that'll be used in the field. With Edge Impulse, we allow you to do that very easily without having to kind of write a bunch of code or do a bunch of plumbing and connecting of different infrastructure. And we also make sure that this is all traceable and secure, that you'll be able to understand, okay, where did my data come from? Maybe kind of what quality of that is that data, and that it, at no point could be, kind of accessed improperly or anything like that. Once you have that data, we have a robust set of industry-leading technology that allows you to train state-of-the-art neural networks. We'll see this live in a little bit, but we have many different optimized and highly effective DSP techniques, as well as neural network architectures, AutoML, and other cool features, to name a few, that allow you to really quickly and without a lot of data science or machine learning experience, still be able to build super robust, super powerful machine learning algorithms. And then from there, we also have a lot of tools around that validation side, testing your model performance, benchmarking it, and seeing how it changes over time, which is really cool. So from here, the other thing that we put a lot of focus on and that we're really excited about is the idea of optimizing a model and choosing your model architecture, your data ingestion, everything around hardware, around your hardware constraints, around your app constraints. As we'll see in the demo, we're able to kind of in a novel way pick a machine learning model that will actually fit and run effectively on the real device that we're using. And we can do this all from our web platform. With kind of that mentioned hardware, this is a great place to jump into the TI board that we'll be using today, and kind of where it sits in the ecosystem, what it's really, really good at, and why we chose to use it for this demo. This board, the CC1352P LaunchPad, is a sub-gigahertz low-cost IoT chip. Now, by being sub-gigahertz, being sub-gigahertz capable, I should say, there are a lot of advantages across a lot of different industries that line up really, really well with where data-driven machine learning techniques are also super effective. In smart home or industrial applications, the added range and ability for sub-gigahertz to go through walls and other obstacles makes it a very robust solution. If you have a smart home security sensor, you don't want that sensor losing connectivity either through, as shown here, a kind of range or signal pathing limitation, or interference from all of the other higher frequency signals that are so common in a home today. Things like Wi-Fi, Bluetooth can all interfere with higher frequency wireless communication protocols, but a lot of these sub-gigahertz protocols are really robust against that. And then it's also extremely low power consumption. And because of the low power consumption, it pairs very nicely with embedded machine learning. One of the concepts that we find very useful with embedded ML is that it compresses the amount of data you need to send over wireless bandwidth by an order of magnitude. You go from needing to potentially stream a live audio recording of what's happening in an area to just only occasionally needing to send a single packet saying this event happened. And that change allows for really, really long battery life devices. And TI has kind of industry-leading, low power consumption in their IoT products, and that is, a perfect fit for that sort of low power, low frequency wireless type of communication. And as I mentioned, this fits in well with a lot of markets where what we do at Edge Impulse, we also see a lot of value. Things such as security systems, logistics, building automation, smart homes. All those things I mentioned are both places where we see a lot of use of embedded ML, and we also see a lot of use of kind of that sub-gigahertz, low power, long range transmission capability. So just a little bit of an overview about the CC1352. It's a very low cost, low power chip. So it's relatively compute constrained. It's a Cortex M4 running at 48 megahertz. And for those of you who are familiar with these sorts of low power chips, this is something where, maybe 5 or 6 years ago, you wouldn't even be able to run an ML algorithm on a chip like this. But now as kind of that technology progresses, these types of very, very low cost wireless chips can run a neural network on them. And that, as we'll see, has a lot of really cool capabilities that it opens up to. It supports dual band, so you can run kind of a BLE interface to essentially connect with your phone, as well as communicating over that more robust long-range sub-gigahertz network. And it supports a variety of sub-gigahertz stacks, things such as 15.4, Amazon Sidewalk, and YSUN. And all of these different stacks are also fully compatible with Edge Impulse, which is really great. And we actually, we have a kind of example code available for working with the TI 15.4 stack and Edge Impulse kind of already ready to go for users. So with that, I don't want to kind of take too much time before getting to the interesting part. I'm going to hop into an actual Edge Impulse project, and we're going to get started on going through kind of the demo use case that I've prepared, and what we're trying to do and how we can design this machine learning algorithm effectively. So what I've got here is an Edge Impulse project. This project, as you can see, it's named Acoustic Anomaly Detection. And what we're trying to do is detect the sound of glass breaking in complex environments with other noise happening. And the data that I obtained for glass breaking, I've taken from a publicly available data set that the link is here. And for a lot of these background noises and kind of just noise of things happening, as we'll see in a little bit, I recorded myself live off the device. And I'll show an example of both use cases so you kind of can get an idea of what it looks like to develop a data set on our platform. If you go to this through this main page, this project is publicly available. So the link will be shared at the end of the slide deck and also in an email to all the participants. So you can access this project. You'll be able to take the data, try it out, maybe add new features, add new types of sounds to detect, or just play around with it and see how it performs in your chosen environment. From here, we're going to be looking into kind of the data acquisition view. And this is where kind of it all starts in Edge Impulse. So this is where we want people to be able to come in here and get data into our platform as easily as possible. And I'll try and show you really quickly. I'll just kind of list off the different kind of methods of getting data to us, and then I'll show some live demos of it. So for any fully supported dev kit, like this TI LaunchPad that I've got here, we support a CLI interface with any kind of host computer that lets you capture live data from the device and upload it directly to Edge Impulse. We also support input of audio, video, and accelerometer data from mobile phones. This can be really helpful if you're prototyping, maybe you don't have a dev board available yet, or you haven't interfaced a microphone with your dev board quite yet. You can still get so much out of the kind of walking sensors that everyone carries around with them in their cell phone. And this is just handled through a web app. You will just go through this link, and then from there, that web app will let you record audio and stream it directly to our platform. Additionally, you can do the same from a computer. And you can also implement data forwarding, a very simple data forwarding protocol with your existing firmware to allow it to interface with an uploader tool without having to do a ton of kind of library integration of any specific, proprietary, not proprietary, but vendor specific ingestion formats, things like that. And then finally, if you are, as I mentioned, working from an open source data set or working from a large database, we support uploading to the cloud via a UI. And so that's where I'll start. I want to really quickly give an example of just what it looks like to process a sample. I've just cherry picked a sample out of my out of the DCA-SE data set that I linked above, which is going to show kind of what it looks like. So you just hit upload. We're going to open our file. So this is a recording of someone breaking glass. So we're going to label it as such. And we're going to put this in our training set. We're just going to upload it. We see that it uploaded. And now if we go back to the data acquisition view, we'll see our sample here. And this is the sample that we just recorded. From here, what I would like to do is I would like to select the actual events that I care about. So in this example, and you can think of this is something that'll commonly happen when you're collecting audio data. You might be saying a word repeatedly, like a wake word that you want a device to detect. And rather than having to sample, restart your recording software every single time, it's often much easier to collect a long section of you repeatedly saying a word or repeatedly saying multiple different words. And so in Edge Impulse, we support that workflow really easily. We do kind of automatic sample splitting, or we'll at least try to. And you can see here, our tool has generated 2-second windows that we can kind of resize around where it thinks there are interesting events going on in the audio sample. I'm gonna add a couple more to cover these other use cases here, these other glass break events. And then from here, we can hit split. And now we've just generated 4 samples from that 8-second sample. And so that's just kind of one common thing we see, and it's a good feature to have. It makes it much easier to kind of record a long sample of data, have the tool automatically split it for you. You may have to do a little bit of kind of moving around the windows, but then from there you have, all of your different actual samples recorded in the platform. And then the other cool thing that we support is, as I mentioned, that kind of Edge Impulse uploader, where I can live collect samples off of this device. And so what I'll show right here is what that process looks like. So at Edge Impulse, we offer kind of a set of CLI tools that you can just install. We have instructions on our website, and the link to that will be shared at the end of the slide deck. But once installed, we have what we call the Edge Impulse daemon, which connects to this dev kit over a USB connection. We can see the USB here. And we can see here that our device just showed up. So let's give it a nickname, TI. And from here, we can just record data. So what I'll do here is I'll just do a short sample of me kind of recording myself talk, just to kind of provide some example background noise. So we'll call this background. And we'll just do a couple seconds. Don't need too many recordings of me talking. And we'll start sampling. And so now you can see on the device, it's sampling. And once it's done, it will read the data off of the dev kit, and it'll upload it directly into Edge Impulse. And we'll see that in just a second. Right there. And so now you can see, and if you want to, you can even play back the recording of me talking. I'll spare you that. From here, I'll go into a bit of detail about the rest of the data that I've collected, because you can see here, we've got about 6 or 7 minutes of this. And if we look at the different background noises, I've got a bunch of different different types of things that I've just recorded that I expect this device to come across in the real world. So I've got things such as people talking, people closing or shutting doors, kind of noise of traffic coming by, all sorts of things that you might normally experience if you're, as I am, sitting in a home office running this device. And so it's important, I'll note that it's important that for applications like these, you want to be aware of, where will I end up running a device like this? And what sort of things will it hear? And what sorts of things does it need to know how to process, know how to label, right? And so that's kind of a key consideration when you're developing a data set like this. But this is a great starting point. If after this you're interested in starting your own project, you can access this publicly. I'll show you really quickly how you can just grab all of the data. You'll go to the public link, which will be shared in the slide deck, and you just hit export. And from here, you can get a hold of all of the data that I've used, and all of it's publicly usable. There's no real issues around licensing it or anything like that. It's free for you to use. And it'll cover a lot of cases, and as we'll see, it's hopefully going to be really robust against kind of the conditions of a standard kind of room in a home. And so from here, I'll also mention that kind of what some of these UI elements mean. So The first thing here is showing a balance of the data that we've collected in different classes. So we only have 2 classes here. And we want, in most cases, to have a good balance between the two. Generally, if you supply the machine learning techniques that we're going to use later on, a lot of data of one class and not very many samples of another, it won't be very good at sampling that class that only had a few samples, a few examples of it. It won't be able to learn to detect that sort of thing. And then simultaneously, we also want a, separate from our training data, we want a test data set that we never look at during training. We never kind of compare performance or evaluate until after the model's been trained. And this is to hopefully evaluate the model in closer to real world data. What would it hear or see once it's deployed? And what's cool is that with Edge Impulse, you can do your training all through our web interface. You can test the data running the exact same model that will be deployed onto the device in the web and get that kind of instant feedback on, okay, this is how my model's performing. And then you can deploy the trained model to just run on the device and kind of see how it actually performs in the real world and get that kind of intuitive sense. Okay, like I think it's detecting when glass breaks and it's not giving me false positives in real world cases. So for this test data set, it's just a separate tab in this data view. You upload samples just like I showed for the training data. And you generally want kind of a 70-30, a 70 to 80% of training data and kind of 20 to 30% split of test data. And that's just to kind of optimize the robustness of your testing against the idea that your model is generally going to perform better the more training data you have. So you don't want to give too much test data and rob yourself of useful training information. So from here, I think, this gives a good overview of the data set. It's kind of these sounds of glass breaking and then various background noises. And so from here, we're going to go to what we call our impulse design tab, where you actually are going to create the algorithm to classify glass breaking from any sort of background noise. So there are a few considerations here and a few options, knobs that you can tweak. So the first thing is that Edge Impulse will automatically detect the type of sensor data that you are using, and it will give you some kind of key base level decisions that you need to make around that data. And so the first thing that comes up here is this idea of your window size. And so the window size is the buffer of audio samples that it's going to run inference on at any single point. So a good way to think about this is that if I'm trying to record someone saying a word and it takes them between 1 and 3 seconds to say that word, I need my window size to be at or longer than that 3-second period. That allows me to detect all of the information in them saying the word, maybe with other noise in the background, and then train the algorithm to pick up that entire sequence. So generally, that's the way you want to think about a window size. It's how long do I need to capture data for to get the information of what I'm interested in. For something like glass breaking, it can kind of vary, but through a little bit of empirical testing, I found that around a second is sufficient for the types of kind of instantaneous glass breaks, followed by maybe kind of the sound of glass falling and kind of maybe hitting the ground or something like that. As you'll hopefully hear at the end of this when we do a live demo from a recording. And then the second one is the window increase, where you're going to be saying, how much do I want to slide that window over across my samples? A good way to think of this is that in something where the start of the phrase is very important, something like saying a word, where the first letter is pretty important information. If you're running a model and you're running 1 second, and then you skip a second ahead and then you run it again, if someone says a word right in between those two things, you will have a lot of difficulty picking it up because that information is split across 2 separate windows. So by lowering the window increase, you're able to slide that window a little bit at a time and properly catch at least one sample where the user said the word, or the interesting event, like where the glass started to break and you get that loud kind of noticeable event. That's the kind of thing that we're looking to pick up here. And then finally, Edge Impulse supports downsampling. So if you're collecting data from a variety of sources, Maybe you've got your phone microphone that's collecting at 48K, but then you've got this low power on device microphone that's only collecting at 8 or 16K. We can unify that to the lowest sample frequency. And that lets you kind of pull data from a variety of sources and just interface with it really easily. So, and also alternatively, if you're in a really constrained environment, lowering your sample rate can lower your power consumption. It can lower how much memory your model needs. So the ability to kind of pull your sample frequency down when you don't need really high frequency, high fidelity data to detect maybe really obvious events like a loud bang, you'll have advantages and you'll be able to kind of save some resources there. So once you kind of configure these baselines, you now have the option to select some DSP preprocessing and then select what type of neural network you want to run to do the classification. We offer a whole host of DSP blocks that you can kind of choose from, and they have their different uses, their different kind of ideal cases. But I won't go too much into detail on this because in the ideal scenario, we're going to let the Edge Impulse platform kind of choose this for us in a way that I'll show in just a little bit. So we're just going to kind of go for now with a default spectrogram. And then we're also going to select kind of just a general neural network. Edge Impulse generally supports two different types of neural networks. The first is what we call classification, where you have a discrete number of events that you want to detect. So in this case, I want to detect background noise and I want to detect class break. So the output is two discrete things. Alternatively, if I wanted to detect, say, the temperature of something based on an infrared signal, or based on estimate the weight of something based on an image of that object, we have what we call regression models, which is a neural network. It's still a neural network, but the end result is a single continuous value. And so you can think of this as situations where you don't have discrete events, but you have kind of a continuous state that you want to predict. And so here we obviously want to be using classification, but just to kind of put that in your mind that we have that option too for those kind of more continuous predictive use cases. So from here, we just save the impulse. And then we can go into looking at what our DSP and other options are within the platform. So here you can see a spectrogram that we're generating based on a background noise sample. And you'll see here, this is kind of what the output of this is. And so the idea of this network is that we're going to generate from our large sample of audio a relatively low frequency, low resolution spectrogram. And then we're going to run essentially an image recognition algorithm to identify the difference between what is a spectrogram where glass is breaking, what does that look like compared to everything else, people speaking, a car driving by, things like that, right? And so you'll see here, again, there are a bunch of different kind of knobs that we can tune, things like, just different parameters about the spectrogram, what its noise floor is, how high of a resolution we are, but we're not really going to touch these because within Edge Impulse, we have the ability to kind of automatically search and tune these parameters to pick what the best value will be at runtime. So if you know the data that you're working with, if you know, oh, I'm working with something where anything below 70 decibels is low noise, you can manually tune this, of course. But if you don't know, if you're unfamiliar with that, our tool can kind of help you discover that iteratively. And so leaving those parameters default, we go into our next step of the DSP block where we generate features. And what this means is we basically create a spectrogram for every single slice, every single window of all of the data that we collected up here. And from this, in Studio, we now have a set of spectrograms. And we also provide you with this cool visualization of how similar the different spectrograms are to one another based on a certain class. And so what's really helpful about this is that if you're looking at a large data set where you need to kind of build that intuitive understanding of, okay, what's difficult to classify, what's easy to classify, we can look at this sample and we can say, oh, this sample specifically might look a little bit closer to this grouping of background samples than expected. And so things like that can just help you build an understanding of, if you get a model and you run some DSP on it, and the model you get is just a complete random ordering, maybe that's not the best DSP to use on that type of thing. Maybe there's some more effective type of processing. Or maybe we can just skip that DSP altogether and just send the raw data straight to the neural network, and where it can learn how to split that up. So this is kind of, it's just an untrained, just kind of initial look at how the data in your project kind of relates to one another. And so basically, the more similar, the closer 2 points are on this graph to one another, the more similar they are. And that's kind of represented in this three-dimensional view. And for those in the know, this uses UMAP to generate, which is just an algorithm for doing this sort of three-dimensional relationship. It uses that to kind of generate this graph. So once we've kind of analyzed this, this honestly, it's pretty well split out. I don't think the network will have too much difficulty kind of analyzing this. We move on to our neural network step. And so here I've already trained this. It doesn't take that long to train. It takes around 5-ish minutes, but just to kind of avoid delaying, I've already trained this ahead of time, and we get pretty decent accuracy. It's around 95, 96%. You can see there are a few it's an even split. It's not skewing too far towards classifying everything as background or everything as class break, but there are definitely some hard samples that are tricky for it to classify. And we can kind of get an intuitive idea of why that might be based on this, the same UMAP graph, where here we can see this is kind of recording near the end of the sound of a glass breaking. And so maybe that's starting to sound more like background noise, just kind of the clinking of glass hitting the ground, something like that. And you can even play the sample, view it to maybe do some additional cropping, or view the spectrogram that it gets generated. So that's all easily accessed through the tool. And then we're also going to get an estimate of how long this neural network will take to run on the device and how much RAM it's going to use, which is really important because on devices, on this device, for instance, we've got around 80K of RAM and around 350K of flash to work with. But you might be running other elements. You might be running a wireless stack, all of which take up compute resources. So it's good if you have an understanding of, okay, I have around 10K of RAM left free, then based on these estimates, you can kind of get that idea of, okay, my model is in range of what I'm looking for. And if it's not, or if the accuracy here is not acceptable, one of the coolest features we have within Edge Impulse is what we call our Eon Tuner. And what this does is, from this baseline of this initial model that I've trained, what the tuner lets me do is select my target device and select different parameters about that device, how much compute time I have, for instance, and then shown here how much memory and flash is available on the device, on the target. And then what it does is it randomly searches different changes to the model architecture in order to see if it can find a better performing model. And better performing can mean a lot of different things, right? If you're working on a very memory constrained device, maybe this device is a relatively low amount of RAM, right? And if we look at some of these high performing models, some of these use a ton of compute time, more than we really want, or they might use more RAM than we have available after we've added in all these other features that we want our real production application to do. We can constrain this. We can select against, okay, what's the fastest model? What will give me the most real-time rapid results? And so here you can see this one's only taking 100 milliseconds to run. This one's taking only like 70 or 84 milliseconds to run. And alternatively, if we're constrained on RAM, if we say we know, and I happen to know, the code that's running on this Launchpad that lets it do data collection as well as run a model takes around 30-ish K of RAM. And so if we see a model here that's taking up more than that, we can constrain our search for things that use a very tiny amount of RAM. And we can select these. And alternatively, also another thing interesting to mention is we can sort based on what classification we want to be the most well scoring or most precise. So in situations where we need, it's really important that we have very, very high performance for detecting glass breaks, but maybe we don't care as much about false positives. We can select for scores that do this. And if you look at this, the models that are top performing here are a little bit longer than our available compute time. But if we go down here, we can get to some that make the trade-off more in the realm of kind of on-device accuracy instead of just raw compute. And we can also filter out these ones that are kind of breaking different RAM barriers or breaking different performance metrics that we don't want. I don't want to take too much more time on this just because I want to leave time for questions. But from here, the next step that you'll go through is the ability to live classify, which I won't show just in the interest of time, but I'll briefly mention. In the same way that we can import data into the platform for our data set, without having to write any code and deploy anything to a device, we can connect that device with Studio, stream data into our sample, and then classify it using the web interface. And so it's not running the model on device yet, but it's running the exact same code that will eventually be on the device. And that lets you, in some cases, you might not be able to deploy to a device yet, but this lets you really rapidly just prototype, try things out. In a more robust environment where you actually want to classify all of the performance across a large number of samples, maybe collected off device or different real world conditions, that kind of test data set can be used here. And you can just hit classify all, and you'll get the kind of results on hopefully more realistic data. The model definitely has never seen before in real life. And so here you can see it's kind of shifting towards it's classifying background very accurately, sorry. But it's mischaracterizing a few samples where glass is breaking as background noise. So maybe that's something by collecting more data, kind of analyzing where it's struggling, maybe in that training data set. Here you can kind of see, oh, some of these samples are again near the end of the window of the sound of the glass breaking. So maybe that's a challenging environment to kind of accurately detect. But in the real world, we'll be able to kind of get an estimate of how this runs by actually running it on device, which we'll get to next. The one final thing I want to mention before I show kind of the live demo is that we have the ability to implement versioning. I just showed a ton of different options, all sorts of things you can change, uploading new data, doing all sorts of stuff, right? And so the versioning tool lets you kind of take a snapshot of exactly the data set, algorithm, parameters, tuner options, and kind of store that. That way you can access it later. Maybe if you suddenly run into an issue where your model starts performing worse after you added some new data samples, you can get back to your old performance and then kind of compare what changed, right? So you just can store a new version. And then finally, we get to our deployment view. So for our deployment targets, you can deploy to a C++ library. This will run on anything, any TI device that's using a Cortex-M and can fit the model that you've trained. But for the CC1352, we offer kind of this fully supported dev board where we have this pre-designed demo firmware that you don't have to write any code for. You just hit build, and it'll take a little bit to build, but then it'll give you just a zip file with an executable that you can run on the dev kit and test out your model's performance really, really quickly. And so you can use this as a starting point to test out performance on device with the real sensors. And then from there move to, okay, how do I integrate this C++ library with my real firmware? And on the Edge Impulse documentation and examples, we give examples of both cases with the TI LaunchPad so that you can kind of build an understanding of kind of how everything all fits together. But for now, in the interest of time, I'm not going to wait for this to build. I've already downloaded this ahead of time, and I'm going to load this onto the device. We're going to quit the uploader tool. And to flash this on the device, you just get a zip file with the pre-compiled firmware. And then we give you a easy to run kind of flash script that just in one click will flash it onto the dev board. And so now my dev board's programming, and you can see that once it's done flashing the device, I can start a different CLI tool to actually run inference live on the device. So that's what I'll do now. So now that that's run, I'll do Edge Impulse, run Impulse. We're going to do continuous. And so here you now see it's just running inference as fast as it can on the device right now. And it is kind of just showing the raw output from the neural network. So it's just kind of think of it as like debug printing what the network is doing. And so, and here you can see the zip file once the new version built. But here you can kind of get an idea of I'm talking and it's relatively, it's not falsely picking that up. But now let's try it on a real example. So I don't have some actual like a glass pane to break. But what I do have is a recording on my phone of someone kind of hammering a tempered glass panel. You'll be able to hear it through my mic. And what's really interesting about this sample and why I chose it is you'll hear they're kind of hitting the panel, but it's not breaking. And then when it breaks, there's a different characteristic sound. And I find it very interesting to see how the network kind of handles that case of a loud reverberating sound that doesn't necessarily correspond to glass breaking. So let's kind of hear that now. Hopefully this isn't too loud, but just early warning. So here's the sounds of them hammering. And you can see there, once the actual glass broke, we got kind of a lot of activity and it started detecting, okay, I think there's a higher probability that a glass is being broken there. And so that's kind of just a instantaneous test to see how this model that we performed works on device in the real world. And from this testing and from kind of some other testing I've done around, it's relatively robust. And from here, there's definitely new data, new context that the device might need to learn about that aren't covered in my background noise data set. But this is definitely a good starting point to kind of develop this type of application, or even maybe substitute in different anomalies that you're trying to detect. That DCA-SE data set has a lot of interesting different samples, things like a baby crying, and they all work equally well with this type of model. So those sorts of things can be added in and tested out on your own with this model really easily. So with that, let me return to the last couple slides of just some resources. So this deck will be sent out after so that you'll have all of these links, but TI has a lot of awesome training material and dev boards. You can buy the 1352 LaunchPad, and as well as other kind of sources for learning to use the TI kind of hardware ecosystem. And then for everything we used in this example today, the project, tutorials on how to get started with integrating Edge Impulse with TI, and some example firmware are all available on our website. So with that, I'd like to do some questions. I ran a little bit long,
Awesome.
but hopefully we'll be able to get through as many.
Yeah, we have quite a few questions, so let's get started. Awesome. How much DSP, this is from David, how much DSP would you say percentage-wise is behind the algorithms versus, say, linear algebra or simple math? And a follow-up to that is whether this is ML is primarily a curve fitting exercise.
Yeah. So it's really interesting, actually, and that's a great question. It relies a lot. It depends a lot on the type of data that you're working with. So with audio specifically, I'll talk the most on this since that's what we're looking at today. Quite a bit, actually, because the networks that run effectively on embedded systems due to compute and memory constraints are generally convolutional neural nets. And so without going too much into the details, what they don't necessarily have is they don't necessarily look back in time on their own and relate different points in time and kind of develop an understanding of that sort of relationship. So what did the past sample look like, for instance? So if you're thinking of that towards, I'm trying to detect a keyword, that's someone saying a lot of different sounds in sequence, or I'm detecting glass breaking where there's an initial bang and then there's kind of that shattering sound. Developing that relationship, the easiest way to capture it on an embedded device turns out to be to take a spectrogram. So you get the frequency information on one axis and you get the time axis on another, and then you just hand that to the neural network, and in one instance it can run on it. So the neural network's still doing a lot because there's still a lot of learning that has to happen. But a big part of that is the effectiveness of the DSP in capturing the relationship between different frequencies and how they change over time. For something like a simple time series sensor, where it's, say, sampling a temperature at a certain time, and maybe you want to predict future temperature, or estimating if there's an issue based on, another example is estimating, if a failure might occur in like a valve or pump based on pressure. Things like that. Oftentimes we don't necessarily need any DSP at all. And Edge Impulse supports that. You can send raw data directly into the neural network and let the network learn all of the features. Because the network eventually, if you train it, can learn to approximate things like filters and things like that. But yeah, for audio, the DSP is doing quite a bit. And then as for the curve fitting exercise, it definitely is. But the important thing to keep in mind is that if you look at other different types of, well, these are still machine learning algorithms, things like traditional regression or things like support vector machines. They don't necessarily work as well in very complex environments where there's a ton of different features. Like with that spectrogram, it's still, a 128 by 500 pixel image. And so developing a model that can effectively do that curve fitting with such a large dimensional feature input is difficult oftentimes for non-neural network-based approaches to do.
Great, thank you. Let's see, another one. What kind of range can you get from a sub 1 gigahertz board?
Yeah, so it often depends on exactly how much data you're trying to send through. But you can easily get over, kind of like in the hundreds of meters range with very low transmit power. So that's the other kind of variable is as you go up in transmit power, you're consuming more power, but you're getting more range out of it. So it can kind of be tuned based on the application. And I think if you go to those TI resources, they'll have kind of the trade-off curve of like, okay, how much power do I need to transmit to certain range under what conditions? So I suggest looking there just because I don't know the exact details, but I think that would give a good baseline kind of starting point.
Cool. From Gary, why did you use spectrogram and not audio MFE processing block for this particular audio type?
Yeah, definitely. So I kind of glossed over a step that I did where just for time's sake, I had already gone through, run that Eon Tuner. It generally takes about like an hour to run, right? So because it has to run all the different range of possibilities. So I had already selected a well-performing model based on the tuner. So that starting point was kind of automatically selected by the tool. It determined that was very fast. That specific spectrogram with those parameters and that neural network was really fast and it was really accurate. So if you go to the public project, you'll be able to kind of see that and check out those parameters. And then you'll also be able to compare that with all of the different approaches that the Eon Tuner tried, which I definitely recommend checking out because it'll be really interesting to, compare and contrast the MFE and spectrogram. So to answer the question, I don't really know. It just ended up working better, right? So which is great. Like you don't necessarily need to know the why of it, I guess.
Cool. All right, from Rod, can you discriminate selecting a particular frequency band, for example, just to classify human voice compared with the rest of the spectrum, wind noise, etc., the idea of filtering just the human voice?
Yeah, so if you look at, we have a block, the MFCC, so it's like Mel frequency capture coefficients. That's a really common way of doing exactly that, of like bands selecting certain frequency blocks that and scaling them such that they match up with human voice. In our base spectrogram block, if you want to, you can select kind of features to, a low and high frequency to kind of isolate features from. We don't really support like doing like filtering out a specific frequency within a spectrogram. But using the MFB or MFCC blocks, you're going to kind of automatically be selecting for interesting frequency ranges already.
Great. What are the challenges and limitations of the current Edge Impulse Studio?
So yeah, I can definitely talk on one particular case that I think is really interesting. So there's two things. So the first is I talked a lot about data set creation, and I think there are even some other questions on this of what do I need to make an effective data set? And right now the platform, we can kind of give advice and give kind of those metrics that I showed, but we can't tell you, exactly, okay, you're missing this sort of thing that is an effect, that's necessary for this model to perform well in your data set, right? And so there are a lot of actually metrics and heuristics that we're looking into for understanding how we might be able to improve that. And that's something we're actively working on. And then on the other side of it, on the testing side, that test data set I showed you, was just similar samples to the training data set, and then it's a short sample of the sound, right? So it's like the glass breaks and that's all that's going on. There might be a little bit of background noise, but that test didn't necessarily include, okay, what if a car is driving by at exactly the moment that the glass is shatters, right? And so in that example, it might work well in performance, but that test might not actually accurately capture that case. So one thing we're actively working on is something we're calling like application testing or tuning, where we synthesize different combinations of background data sets and event samples. Or you can record a real world like stream of say like 24 hours of just this device sitting in the real world collecting audio data. And then we can analyze that and we can look, okay, how does this actually perform at detecting a sample in the presence of this background noise? What's the false accept rate? What's the false reject rate? And how can we tune the post-processing of this model? So, we didn't do any post-processing in what you saw today, but you might want to average together multiple results of the network, things like that. How can we tune that step in order to get the best real world performance? So I would say those are two things that are active challenges that we're aware of and that we're working on and have planned solutions for coming in the near future.
Awesome. So what is the hardware to acquire sound on the LaunchPad?
Yeah, so the hardware on here, I don't have the exact model name of the microphone, but it's a small I2S mic that's included with there's a audio booster pack that we actually advertise on our if you go to the documentation on our website, we show, okay, you need this booster pack, you plug it in the LaunchPad, and then that collects audio at a 16 kilohertz frequency, and it's running inference off of that. So for the exact details, what I would do is I would go to getting started today. Oh,
sorry, is that the board that was on the landing page for this webinar?
Yeah, yes.
Okay, I just put the link in the chat, so you guys can check that out too. Sorry, David, go ahead.
No, that's perfect. Yeah, so check out the specs there, and that'll give you the exact idea of like, it's noise floor and things like that.
Awesome. All right. Let's see. There were a bunch of them in the chat. Let me see if I can go try to find a couple other ones. Is there a guided tutorial of how to deploy a model on an Android phone?
Yes, there is. So if you go to the main link of our Getting Started Docs page, if you just go to our main website, kind of our top level Getting Started guide does the same thing for a mobile phone, and you can go through the full tutorial just the same as you do with any of our supported dev kits. It's just using the phone web app to collect and run the impulse.
Great. Is there a way to train the model without using the background samples? In reality, the background samples can be infinite. If your model gets sound which is not on your sample, maybe it can make bad predictions.
Yeah, so that's a great question. So there are a couple of approaches you can do for this. The first thing is that while the samples that it'll occur in the real world might be infinite, you can constrain that case through two means. First is just what realistically will be included in the environment. If that is a very large set of things, one thing you can do that we often employ is we'll do simple kind of unsupervised clustering along with a neural network. And so the idea there is you have a neural network that's trained on two classes, say background noise and glass breaking, right? Then I have an anomaly detector that's just doing unsupervised clustering, and it has all of the data that we've collected in our training set, regardless of label, and it's kind of grouping that together and seeing how that relates to one another. If I then get a sample on device that looks nothing like my training data from any label, then that anomaly detector will be able to potentially flag that as an anomaly, something that the model isn't prepared to deal with, and the application logic on my device can handle that accordingly. Another way that we're working on actually is this idea of you can, we do this already for images. And so for a very large data set of images, you can get things like publicly available data sets like the COCOS data set, where you can take a ton of images from many, many different contexts, and you can learn on those. And then you can do what's called transfer learning, where you retrain the last few layers of that model based on that image. So that's something we offer around images, where you do get a lot more variation. But besides that, anomaly detection for audio and just kind of collecting real world data that is actually what you'll see, what the device will see in the real world is very effective. And you'll end up with pretty robust models from one or both of those in combination.
Awesome. Well, it looks like we have hit our hour mark, so we don't have any time for any more questions. But if you didn't get your questions answered, there is a forum at edgeimpulse.com. So you can go to forum.edgeimpulse.com. And I put that link in the chat a little while ago. So thank you so much, David, for joining us and for the demo. And thank you, everyone, for joining. Have a great rest of your day.